started with Yifeng is going to do, Yifei is going to do her presentation on transformations and regression. Just a second. I'll write up a little bit about schedule. So we can go over that. So let me just say just about schedule, and then you can start with her presentation. This was the previous time, right? There. So on Friday we'll continue with talking about regression, diagnostics, selecting variables, and so on. Monday is college break, so we won't have class then, and we'll come back on the 9th and continue talking about those topics. 9, 10 kind of go together, like 7, 8 kind of go together, so they're similar. We won't have a homework due that day because of the breaks. On the 11th, we're not going to have class. The Vermont Genetics Network Research Collaborative has a meeting that day over at University of Vermont, so I'm going to go to that. That day is the Pi Mu Epsilon lecture, so I hope many of you attend that. That would be a good chance to see mathematics and statistics and combinatorics and modeling in an applied setting. And then we'll come back the next week and continue and have a homework due in this week. Yes?
So when is homework 5? Because it said the 11th it was due, but if we don't have class, when's homework 5 due?
So is there a homework 5 now?
Or homework, I think you mean homework 6. Because we just did homework 5.
We did.
Oh, wait.
No,
Yeah.
we just did homework 4.
So homework 4, I'm returning this one.
Right.
And is there another one that's posted?
Yeah, it says, hold on, I'll look at
Well, it might be, we can talk about that. If there is a confusion about it, it's fine to do the work. A lot of it is. But if there's a discrepancy between, so I posted one that I was thinking would be due today. And if something didn't get put in right in Canvas, we'll just do an extension and people can work on that. So sorry if that,
Okay.
sorry if I programmed something wrong in the Canvas for announcements and so on. But then that one can be done over this next period, and then this one would do some of the 9, 10 chapter material. So sorry if that was a confusion, but we will. It's there. I can wait to post solutions, and a lot of it's investigating data anyway. So you can still have an opportunity to do that one. So, but anyway, that's the plan. So another one is not posted quite now. Zhengji Lin gets to do the next of these presentations, and so that would be in a couple weeks because of the fewer classes that is coming up, right? But today we're going to start out with Yifei Zhang, Lana's turn to do a presentation, so come on up and let's see if we can make this big. You can tell us about examining the data in a linear regression model. So you can either use this to click along here, or the arrows, however you want to do that. So, great. I think if you just click on it, I think it will move one. Oh, okay. Okay.
talk about using the linear regression model to examine the data. So the regression model equation should look like this. And it's the model is used to compare the relationship between one or more independent and dependent variables. So the simple regression model should use for one independent variable, and the multiple regression model should be used to compare more than one independent variable. So the fields where the linear regression model usually applies will be mathematics, epidemiology, trendline, economics, and finance. So the data set used for this presentation contains information on a study of the effects of a predatory intertidal crab species on a snail population, and the researchers measured the mean of closing forces, which stands for the closing strings of claws of the crab, and the proctus height, which stands for the proctus height of claws of the crab. And on the several crabs of 3 species, which are these species. So the test I split the test into 2 parts. The first part we're testing on the overall data set. So these histogram, the left histograms shows the shows without the log transformation, and on the right side it shows the data, how the data looks like in after the log transformation, and it looks like all the right plots has a better shape after using the transformation. Oh, so these 2 are the regression equation for the data set, and both p-value is very small, and I also find out the statistics, residuals, correlation t-values, degree of freedom, and the confidence interval. And I also find the prediction value when the height is around 8. So for the first one, I got the 9.99 around this range, and the second one I got a negative prediction value, which is around between this range. So, so these 2 shows the one. This one shows the original data set, and this one is the one used after using the log transformation. the points look almost the same in two plots. The second one shows shows the linear relationship more clearly. So for the second part, I used the Hamming data set, which is the first species of that crab. So same as part one. First, I show I find out how histogram look like before and after the log transformation. It seems these two don't have very significant difference. And also here, I did the same thing as the previous one. So these are the equation for the linear regression model, and here both prediction value are positive, and except this one I think is more accurate because the range seems smaller than this one. And the plots I found for this small data set, it looks all the points in both plots are spread everywhere, and it's pretty hard to find there's a linear relationship in this plot, but it still have one. Conclusion. So the hypothesis for the whole test is these two, and for part one, I think we should reject the null hypothesis because the t-value is less than 2.04, which is the t n2.
So the t statistic or the t critical value? That one was significant, right? The first one with all the data? Yeah.
So for the first one, I think the log transformation is not recommended to use because when I find the prediction value, it's negative. So for the part two, according to the results, is that the t-value is larger than 2.03. So the null hypothesis should not be rejected. So for this one, I recommend the log transformation because I think the prediction value this one is more accurate. And two parts of the test don't have the same hypothesis to reject. I think maybe it's the data, there's not enough data for the high change test.
Good. All right. Thank you. I think you can just discard. Right. But any questions about? So, with the predictions, did you take the predictions on the log scale and exponentiate those to get the numbers? I wonder if you did that, because I think if the negative predictions might be on that log scale. Right? So you might want to exponentiate those to get them back on the positive scale. That's okay. I mean, that's a detail that we could. I wasn't didn't notice before, but maybe you need to exponentiate those to get back to that scale, right? But yeah, so did it look like logs were particularly needed in this case, or useful, or maybe there's a biological reason that, some biology of how these things relate together is supposed to be on a multiplicative scale. Taking logs makes some sense, but yeah. Great, thank you very much. So sometimes examples just don't necessarily show as strong of relationships or things, and that's fine. That's just what happens sometimes. I think that's one thing that's going on with this example that's kind of interesting, perhaps, is you can get, when these kind of three crab species are together, you can have something like X and Y. You could have one group here that has almost no relationship, and another group up here that has one, and another group up here that has one. And so when they're all together, right, there's a pretty strong, significant relationship. But when you get, if you did each one, the sample size would be smaller, like Yifei said, and that can make it less significant. But it also could be flat within a group. Right? And crabs, if you take people by educational levels, those just out of college, those with master's degrees, those with PhDs, and they look at a relationship of some variables, you can get different relationships in the different groups, but when they're all combined, it can do something completely different. And if you take something where you selected part of the population, so if this is one example that my advisor put in one of his papers is like an undergraduate grade point average and score on LSAT, law school SAT test. Generally, in the population taking this, there's kind of this positive, relationship that the people with higher undergraduate GPAs generally have higher scores there. But what happens? You take the people who get into law school and then look at the relationship. Right? Who gets in? People with very high undergraduate GPAs, very high LSAT scores, or something where it's not too low on those. So once you do that selection on the population, if these people get in, right? And so that can kind of destroy some of the relationship because you've lost this tail that's low with both. So if you try to predict undergraduate GPA and LSAT scores in just that subset, it probably is not going to be as strong as the entire population. Same thing with the crabs. You select a subset and the relationships might go away. So it's not only the biological or whatever logical relationship you think of, but which population is it and have they been selected in any way to do that. So I think that's partly what's going on in this crab example, why overall you get such a strong relationship and then almost nothing in the other groups. All right. Well, today I wanted to look at, and does everybody have, not everybody has their assignment handout. And here we go with that. Thank you. To look at something in regression, talk a little more in detail about some of the things with analysis of variance table or comparing regressions, kind of make this transition into looking at multiple predictors. So primarily we look at a data set and then write a few things on the board to do that. And the data set we'll look at is a data set on spruce trees. So these are black spruce trees. This is actually a data set that's in the book we're using in Statistics 252. And we attach it so we can look at there. There are a number of trees. So let me look at the header of that data set. And they have the height at time 0 of the tree and the diameter at time 0. And then 5 years later, they're looking at the height of the trees and the diameter of the trees, and looking at change, height versus diameter change. And it's an experimental setting where some trees are given fertilizer and some are not, right? That's this variable, right? And some are grown where there's other competition. And the other ones, they kind of remove the other brush and things around there, so there's not other plants overshadowing them or growing near them. Right? So it's an experiment in that sense within the natural growth. Right? And we could ask a question like, are diameter change and height change, related. Right, that's the one we're going to do. I was debating which ones to do, but yeah, height change related. So to start looking at that, we can look at a plot. Oops, I had to make that big. Right. So here's the plot. Right. Diameter change and height change, and it's a pretty strong relationship. Right? The trees that are growing more, growing taller, are also getting there. Right? So you wouldn't necessarily, I suppose, think about predicting one versus the other. Depending on your context, you could go either way. A correlation might be just of interest. So this one has a correlation of 0.9. Right? The correlation test is a confidence interval that's 0.847 up to 0.97938. For that, and a hypothesis test is the correlation 0 or not is strongly rejected. Right? Because the t statistic from testing is the correlation 0, right? So the right. So the correlation test is testing is the population correlation 0 versus not. And we look at the sample correlation, and it's converted to a t statistic, and we compare that to a t with n minus 2 degrees of freedom to get a p-value. And part of what we're going to look at today is how the results from this correlation test compare to the results from the linear regression, and then the analysis of variance table that come out of that. So we want to kind of point out explicitly where things are the same and would be calculating the same things. Right? So in this case, there's clearly a. I'm going to close this. I want my thing open. Okay, that's what I was doing. This one. So I'm going to go back over here. Right. So if we have that correlation test here, this t-value 17.5, this p-value that's very small, and if we run the regression, now height on this one, this is some of the output we get. And what do we notice that's similar? We're getting that same t-value in here. Right? So with the t statistic that you get from that correlation, testing that ends up being equivalent to testing that is the slope 0 or not in linear regression. Right? So if we have the simple linear regression model plus an epsilon, and we test is the slope equal to 0 or not. Make this one look more clearly like the Greek letter rho. This t statistic was the estimated coefficient over its standard error. That's going to be equivalent to this t statistic, and again, it's going to be compared to a t with 2 degrees of freedom. So these give the same p-values. Right, we have the same statistic value, the same t, and then the same reference distribution. So it's the same tail area, and you get the same conclusion. So the significance of correlation between two variables is the same as the significance of predicting one versus the other. You could switch x and y. In this case, it's going to be the same. Yeah?
Can we go back to the code? I have a question about the code.
About the code, yeah. Sure.
So what's the difference in this regression output? What's the difference in the first row in terms of the estimate error, t and p?
What are those in there? Right, so there's two. There's an intercept, and then this is the one that's the slope.
Okay, that's the one.
And so it is giving two tests. This one is giving the test of the slope, right? And this is testing whether the intercept is 0, right? And, this is height change versus diameter change, and so you wouldn't necessarily have to have a 0, 0 point in there. And I don't know if the intercept would really be of interest in this case. Because over 5 years, if a tree doesn't change in diameter, I guess it's dead or something, right? So we might not focus on this one, but in some examples, you're interested in that intercept, that base type thing, right? So the other one, the first line in code, is testing whether whether the intercept is 0 versus not. If this is true, then our model is just beta 1x plus this. Right? If beta 1 is 0, this one, if beta 1 is 0, this says that our model would be y equals beta 0 plus some that. And then there's no systematic change from x, and x is not related to y because as x changes, y doesn't change in any way under that model. Right? But this one says that that it goes through 0, 0, and there's some slope to this line, and that's focusing on that. Right? So the t-statistic for testing this one is similarly the estimate of the intercept from the least squares divided by its standard error, and again that has this t minus 2 t distribution in minus 2 degrees of freedom t distribution. So we're going to compare that. Are we out in the tails for that one, for that test? Good. There's some other stuff that's in here, right? That comes out of that. There's this residual standard error, multiple r squared, and this f test. Well, let's see where those show up explicitly again. So if you run the ANOVA, it gives you analysis of variance table and these different parts here. Right? It's a very small p-value. This test, this ANOVA table and this f test here is testing the same thing. Right? So from the ANOVA table, the ANOVA in regression, null hypothesis that this one's testing is also that the slope is 0. Do we really need 3 ways to test the same hypothesis? No, you really only need to report one. It's really going to give you the same conclusion. Right? But as we go on to multiple regression, then these f tests and the things, there's more flexibility that we can get from doing it this way. Right? So this one creates an f statistic, which is the mean square for regression over the mean square for error. In simple regression, this f statistic you can show with going through the algebra of it all, that this is the square of the t statistic. It works out that way. You have kind of the standard error parts, had the estimate of mean square error in there divided by something else. And if that thing that's in the denominator is put in the numerator along with the squared coefficient, it works out to be the mean square regression. So you're going to have these two things, this ratio, and do the algebra, and it works out. So this is the one from the t-test of our one here. And this thing under the null hypothesis is distributed as an f distribution with 1 and n minus 2 degrees of freedom. There's kind of testing one regression coefficient up here. There's n minus 2 degrees of freedom for the error. And it turns out that this f distribution is actually the square of a t distribution, right? Squared, right? So you take a t distribution and you square it, and the areas that were outside, in either tail are now in the upper 5% tail of the f. Right? So it's the t distribution with n minus 2 degrees of freedom. You take this 0.025 tail here and this 0.025 tail here, and you square all the t values. That's t minus 2, n minus 2. Okay. If you square it, the f is like this. The square of this value ends up being the cutoff here, and this is symmetric, so the square of this one is also up here. So we're just looking at this one tail up here. So we're going to reject that this f value is very large, which indicates that the mean square regression, the variability caused by the regression, is large relative to the discount variability about the line. Right? So you can check that out with a numerical example, that it works. So I'll just look at this here. So if you take this, let's see, 17.48 was the t-value, this large t-value up here. If you square that, you get 305.83, which is just about that value except for rounding, an F statistic value. If you, the sum of squares, the total sum of squares is 8668. And where's this value, the 0.81? Oh, that's this thing, r squared, right. So r squared is another connection, right? So r squared is used to describe the percent of variability in y that's explained by the regression. So this r squared value is between 0 and 1. R squared equals 1 if the correlation is either 1 or negative 1. Right? R squared is 0 if the correlation is 0 and there's no linear relationship. Right? And r squared gets interpreted as percent of variability in y related to x, related linearly, right, to x, so through this straight line. Y and x might be highly related, but if it's curved or highly nonlinear in a way, r squared won't be so high. Doesn't mean that there's not a strong relationship. In some things, there might be kind of a threshold model, like you get some exposure to something up to a certain point and nothing happens, and then you cross over and boom, something there's a big jump. That's a strong relationship, but it's not a linear, constant, increasing one. And r squared is calculated as the sum of squares for regression over the sum of squares total. And in simple regression, this ends up being the square of the sample correlation. Correlation and the regression slope kind of had the same numerators. There's a lot of connections between the problems. And so this measure of the degree of linear association goes between -1 and 1. And if you square it, it ends up being this. So you can work through the algebra for it, and you can see it in the problems. So if you have different x variables trying to predict y, the one that has the higher correlation, the more extreme correlation, and the higher r squared near 1 is doing a better job of predicting. Right? You can have large r squareds or small r squareds, and it's not necessarily the same as significance, right? So you have a small sample size, you might still get a pretty good r squared value away from 0, but if it's a small sample size, it can be still non-significant. Or you can have a very large sample size, and a tiny change in slope can be significant, but r squared might not be that high. So they're really different things. So let's look at one more calculation of this stuff. So that was the f value. The total sum of squares was 8668. And so if we take the sum of squares from the regression and divide it by that total, we get about 0.81, which was what's reported up here as this r squared value. It's called multiple r squared. Eventually, we'll add more variables, and that will keep going up because we'll be explaining more with more predictors. But anyway, that's there. And it's a square of the correlation. So if we went back to the correlation of 0.9, if there's just two variables, I know that the correlation is going to be, that the r squared is going to be about 0.81, right? Because the correlation is 0.9, right? And that connection is there. The other thing that's in here, right, that's mentioned here, is that here's this residual standard error. Right? That residual standard error from our regression model is going to be the estimate of sigma, right, the regression. So sigma squared. There is in R, so residual standard error is our estimate of sigma on that, right? So it's the sum of the yi minus yi hat squared over n minus 2, and the square root of all that. And each of these things is the ei squared as the residuals. Right? And from the ANOVA table, so just from the regression, we can calculate predictions and residuals and get that number, right? From ANOVA, right, mean square error is the sum of the yi minus yi hat squared, which is the sum of squared error. And you divide it by its degrees of freedom. And so this thing is exactly the square of that. So the regression output gives you it this way, but you could get it from the ANOVA output as well, right? So we'll look at that just shortly. So in this, that's the R squared one. The residual mean square error was 23.1. So the square root of that is 4.806, which is just about the residual standard error that's reported up there. And if we did a plot of, the plot of, let's see, this is our regression that we're running. We plotted the fitted values on that axis and the residual values on that axis. So a line, a horizontal line at 0 to show that where it is. The residual standard error about 4.8. If you put AB lines in at 4.8, 4.8, 9.6, negative 4.8, and negative 9.6. And let's do the dotted ones. There are the 0 plus or minus a couple residual standard errors. Right? And it covers most of the range of the data. Right, but there's a couple of points that are a little bit further out. But this model fits the regression picture quite nicely. And so that describes its variability. Look, and you can see that it's more concentrated in the middle, like you'd hope, and a little bit less concentrated out there. So this one fits the regression model pretty well. All right, so those are some of the correspondences that are there. There's some relationship to if you do the squares of residuals. Right? If you just took the residuals and took all those squares, you would get the number that is the sum of squares residuals that's in that. So here's this ANOVA 16.147 rounds to the 16.15, and so that command gives you the sum of squared residuals. So you take all the residuals off of that regression, square them, and you get that. Okay? Now, you can't just take the standard deviation of those residuals, though, and get the mean square error, right? Because it divides by degrees of freedom, and not by n minus 1. Right? So it's going to be just a little bit different in there. So if you did the standard deviation of those, right, you would, of these things, you get a number that's a little bit less. Because it's dividing by the 71. There's 72 trees, n minus 1 is 71. But what we actually want to divide by to get that mean square error is degrees of freedom of 70. So it's just a little bit different. So those are some of the relationships that are in there. But we could use this kind of output to look at what's the best predictor of change, right? There's several variables in the data set, and ultimately, often in regression, you're looking through possible predictors and building a model to try and explain what's going on. So which are the best predictors of height? If we do correlation, the quantitative variables were height 0, height 5, diameter 0, diameter 5, the diameter change, and the height change. I put them in this order, so when I run this command, and I'm going to make it a little easier to read, so let's round these things to, say, 3 decimal places. Right? Maybe we'll do it to 2 decimal places and try to get it all in one line. Oh, it's the variables names that are so long that is causing this more than anything else. If I manipulate the screen, there you get them all on one. Right? And so if we're trying to predict height change, these are the correlations of height change with the other things. And of course, it's correlated one with itself. And we've been using diameter change. But is that the best variable in terms of correlation? Right. It looks like the height that it was at 5 years is the best predictor of that change. Right. So looking at correlation, if you want to do the thing that most highly predicts the height change, it could be that one. Now, if another one of these variables coming out, was negative 0.99, it'd be a negative one, but that would still be an extreme correlation. So you'd use something that's the strongest negative one. If it's more extreme, closer to 1 or negative 1 than the other one. Diameter 5 is not quite as good, so correlation would suggest we would do that. But would that be so interesting to do? Would it be so interesting really to look at height change versus the size that they are at 5? Maybe you can figure out a context where you want to do that. But change from 0 to 5, and we're predicting it by what's happened at year 5. It's kind of predicting an outcome at year 5 with something that happened at year 5, and in kind of an experimental setting where things start at 0, kind of using things that come at the end to predict something else at the end, in many cases is not quite as interesting. But if you did want to pick the variable that has the best predicted value, it would be the height 5, according to correlation. We might look at some of the variables that, I look at these correlations for some reason. There's the height zeros, height 5s, and the changes. I was just kind of curious to see what the magnitudes were of these changes. So the heights, I thought, if all the heights started exactly the same, well, then height 5 would be growth. Right? So if these all started at 14 centimeters in height, and then we're looking at growth, well, of course, then growth is exactly going to be correlated with that 5. But there was some variability in the height 0. Still, I don't think it's extremely interesting to predict the change in height based on the endpoint that you already have. What we might be interested in scientifically in an experiment like this would be predicting, say, the height at year 5 based on how things started. And then there are some experimental variables. Right? So even if we have some other variables that are good predictors, scientifically it might not be too much of an interest of generating a hypothesis or showing something. Right? The bigger trees grew more. We know the bigger trees grew more, so but maybe that's not quite as interesting. So if we just look at, let's see if this will work for us here. Height 5, there's height 0 and diameter 0. What's the height at year 5 versus the 2 baseline variables? Is there much of a relationship there? So height 5 is on the y-axis of these two, and versus height 0 and diameter, these plots are not necessarily going anywhere. Right? There's maybe a slight increase here. It's hard to see whether you would have much more than a flat line in this one. So those two don't really look so good. The correlations between height, say I put height 5 over here on the end so I can just read across this. The correlation of height at year 5 with height at year 0 is 0.22. So this plot up here has a correlation of 0.22. There's a moderate positive correlation. Versus diameter, there's a very weak one. There is a positive correlation of 0.04, but I bet that would be clearly not significant, given that we don't have a enormous sample size. So let's just plot that one a little bit more. That's what that one looks like. If we do the correlation, it's 0.218. And the correlation test of whether it's 0 gives us a p-value of 0.065. Not quite significantly different than 0. The confidence interval for the correlation goes a little bit below 0. So at a 5% significance level, we can't say that these things are correlated. Now you might think, right, the taller it is, the baseline period, the taller it would be later. Maybe in a larger sample, you might envision that you would see a significant relationship because biologically you don't think that happens. There's a student here a couple years ago, Rebecca Rouleau, who did some work with trees and had a summer internship with people in Wisconsin. And they were measuring heights of trees and whether the trees were infected with things. And some of the trees they had actually got smaller over time. Well, if a tree died and was replaced by a shoot, then they started measuring the new shoot. So the whole data was kind of complicated to deal with, right? And figure out which data points should you keep, right? 'Cause, there's measurement error too. So maybe people didn't measure the same tree. There's 100 trees out in a plot. They're supposed to be numbered or marked, but it's kind of hard to keep track of it all. Other than some of them died and grew again, and so there was some data challenges beyond actually getting that type of data. So this was not quite significant. So if we run the regression of the height 5 and height 0 as the predictor, we should get similar things. Right? So this, let's go to this version of it and adjust this so we can see it. Right. If we do the test for height 0, the slope associated with height 0, right, we're getting the same t-value as we should expect. Oops. And we're getting the same p-value as 4. So whether you do correlation or the test versus the single predictor, it's not quite significant there. And if you, there's that summary, if you did the analysis of variance, f-test, again, you're getting the same p-value, and 1.87 squared turns out to be 3.5. So whether it's significant or not, you're still getting the same correspondence of the test statistics, the p-values in this case, right? How about these experimental variables? There are fertilizer was either given or not given, and then the trees were either growing with competition or no competition. Right? And there was 18 of each. Right? So there were 36 with fertilizer, 36 without, 36 with competition, 36 without, and it was crossed like that and balanced. Right? Is there a difference by fertilizer? Here's a box plot comparing fertilizer. Fertilizer seems to make a pretty strong difference in these things, right? Competition, right? Competition decrease. That's why you weed your garden, right? So because the competition takes sunlight, takes water, and other nutrients. If you paste together the fertilizer and competition letters, it creates a string that has the two letters together. So you can use that kind of trick to look at all four. Let me make it just a little bit wider, and maybe we can see everything. Yeah. So this is the four groups that are created. Fertilizer with competition. Fertilizer but no competition is the biggest. Right? No fertilizer competition, no fertilizer, no competition. So no competition is doing better than competition with or without fertilizer. And I think fertilizer is doing better than no fertilizer with competition or without. Right? So they're kind of the same additive effect almost of fertilizer or taking away the competition. Right? So we have these four groups. Right? So we could do analysis of variance. Eventually we'll do two-way analysis of variance, so we could have two sets of variables defining the groups. But we can do a little bit already with this. Right? So we have a t-test. Right? We could test, say for the fertilizers, is there a significant difference between the average height at year 5 and the fertilizers? This box plot doesn't naturally put on an X label. It'd be nice if it did, I guess. You could make it do that. So here's, oops, that's the Y label. The vertical label. So putting it up here, that's the height at year 5. So that'd be a little bit nicer to have that there. The t-test, that's kind of a big output, so I'll just show it from the file here. If you do, variances look reasonably equal to me, so we compare this is equal. We get a t statistic of 7.29 on 70 degrees of freedom, and the p-value is this very small number. So there is a significant difference between the averages there. Now, can we get some of that same results with regression? And the answer is yes. So this is kind of a funny thing in a way. So fertilizer has values of F and NF, right? They're not, right, zeros and ones, they're not numeric. But if you put them into regression, it knows it's something called a factor. It knows it's not numeric, and these F and NF indicate groups. Right? So it gives us this regression output. Right? What do you notice about this output and the stuff that's coming out of the t-test? Some things are similar, right? P-value is, yep, is going to be the same p-value, right? The t-statistic is the same t-value down here. Right? The intercept 52.98 is the average of X. So, and this is the fertilizer group. Right? So the average of the fertilizer group is that way. Right? And then the difference between these two is 14.7. So what this is doing, when you put in a factor variable with the two levels in there, what R is doing, this would be called an indicator variable. So xi is given a value of 1, in this case in the fertilizer group, and a value of 0 in the one that's not, it's the other way. It did it alphabetically. So it gives it a 0 for fertilizer and a 1 for not fertilizer. And then we're fitting a model in here. It's calculating the coefficient estimates the same way. It's just all our x's are 0 or 1, right? We don't have an assumption that the x's are normal or even continuous, right? We just have an assumption that the y is conditional on the x's follows some normal distribution. Right? And so if we have a tree that's raised with fertilizer, its estimate is just beta 0 hat, because xi is 0. If it's not with fertilizer, yi hat is beta 0 hat plus beta 1 hat, and the xi is 1 there. Right? So the coefficient, this so-called slope, really turns into a difference between the two means, right? And if we test the null hypothesis that beta 1 is 0 versus an alternate beta 1 does not equal 0, this is equivalent as saying that the mean for the fertilizer group is the same as the mean for the not fertilizer group, or saying that there's no difference between them. And under the linearity and normality, we get the same test results using regression or this t-test. Right? Algebraically, it all works out that way. So kind of neat that it comes out the two ways. You know, both of them are based on normals, constant variance, and so it gets the same results. You could do ANOVA of that and it would give the Now, if you try to do that with correlation, you can't do a correlation between a numeric variable and fertilizer. So the fertilizer had those two values. Up here in the environment, fertilizer is called a factor. It might also be called a character string. Right? The fertilizer values are just these F's and NFs. So you can't do that. What you can do is create a logical value. Right? So if you do fertilizer equals fertilizer, it's either true or false. And R interprets the trues as ones and the false as zeros. So it will take a correlation, 0-1 correlation. It's not the usual correlation that we think about, right, between a continuous X and a continuous Y, but it's just doing the correlation calculation with some X's being ones and some being zeros. And if you do that for fertilizer, there's a positive correlation because the fertilizer average was higher. If you do a correlation with NF, it's a negative value because the NF was lower. Right? And so depending on which one you call 1 or 0, you switch positive to negative. If you square that correlation, you get the R squared from the regression. So about 43% of the difference in these is related to the difference in means, which is pretty strong. What we'll move on to, and on Friday, right, is thinking about multiple regression. Right? Because in this, there's two experimental factors, there's the height at the initial thing, diameter at the initial thing, and all that could predict change. Right? So in R, to put in multiple variables, you type a command which lists the two variables, and it will give you three values here. Right? So this output that's coming out of that is estimating a regression line. So going into multiple regression. With these two variables, call one x1 and x2, we're estimating an intercept and then two slopes. Right? In this particular case, each one of these is either a 1 or a 0, indicating one of the groups. Right? And so our equation in this case, toward the back, is multiple regression. There it is. 47.4 plus was a minus 14.77.43. And this one is an indicator for no fertilizer. That's how to read that, fertilizer NF. So if it's a value of NF for fertilizer, it gets a negative, plus a 10.92 for no competition. So if there's no competition for the growing tree, it grows better and gets bigger. And then it gives you outputs for three hypothesis tests. You can do a hypothesis test, is beta 1 equal to 0 versus not? And over here, is beta 2 equal to 0 or not? And both of those are highly significant. Right? Both of these tests are not really the same as if you had just tested one variable at a time, because everything was computed with both variables in there. So given that that competition is a predictor, is NF 0 or not? Is that slope 0 or not? And this one is a test also. Given that fertilizer is a predictor, is the second slope also 0? So there's a little bit of difference, right? These could be not significant, but it wouldn't mean that they're not individually related to the outcome. But given the other thing that's in there, maybe they aren't. In some problems, in some data sets, there's several variables that kind of measure the same thing. Right? So if you did multiple measurements of blood pressure, multiple measurements of diastolic, systolic, a bunch of other things at baseline, and put all of those into the regression, some of them won't be significant. That's because you have multiple things in there kind of measuring the same thing, and they're kind of redundant. In this problem, we could say, in addition to that, we'll talk about a number of things changes. R squared gets better. Talk about adjusted R squared. A little discussion of that there. We can also have interaction. Maybe having fertilizer with no competition really gives you an extra boost. Or having no fertilizer with competition makes you go down even farther. And so there's this interaction term here. And once you enter that, you get a test whether there's an interaction between these two variables in terms of predicting y. And that's not significant in this case. So we'll do fun stuff like that and look at the meanings of these different things again, and look at more checking of assumptions in that multivariate. So it seems like there was some confusion about the homework 5, and I know a couple of people needed extensions for the other busy work. So if you have it now and want to turn it in, I'll take it and grade it. But if not, doing it by Friday would be great. But if things have loaded up and it's just impossible, let me know. Mostly it's individual learning for doing the homework. I think in this class there's a lot of that. So was it a Canvas issue that it was kind of on the wrong time frame, or?
Well, I was like looking at the schedule and everything said it was due October 11th. So I didn't look at the file because I had a lot of other things.
Sorry about that. I'll try to update that.
Literally.
Yeah, I'll try to update that and get it cleared up.
Thank you.
Thank you.